Hello everyone. Right now I'm going to teach you how to derive the e-field a distance z on an axis away from a ring of charge with radius r. So to set this problem up, this is what we got. We have a ring here with lambda as the charge, a radius r, a distance z away from it on axis. The main points here are going to be this theta right here. That's what controls the r. The dq, which is going to be our point here, which is equal to lambda ds, which is going to be a specific amount of charge on a small section of it, as I drew there. ds is equal to r d theta, which is like an arc is equal to r d theta. And we can just plug that in, substitute this ds for dq equals lambda r d theta. We're going to be touching this phi right in here quite a bit as this tutorial continues. Alright, let's get to the derivation of the e-field. So I wrote it up again right here for reference purposes. So to start things off, let's go ahead and write just a general e-field. E is equal to k q over r squared r hat. So we want to make this apply to the ring here, the circle. That's the problem. So first of all, we're going to look at this line of charge right here, dE. That's like the specific line of positive charge engendered from the ring that is passing through our observation point at a distance z. I didn't write that on there. Z. Just like that. Make this a little bit bigger, a little more pronounced. That's our main point there. There are x components and y components of the said line of charge. So if we imagined for the y components of this, if there was a line of charge like this, there's a y component down. Let's say there's a line of charge moving through from the bottommost point here. That y-intercept would be the opposite, pointing upwards, the opposite of this one. If we moved all the way around the circle, the y-intercepts would cancel out. So later on, we can simply say, or even before we even start the problem, let's just say the y components cancel out due to symmetry. That's going to make this problem much easier for us, because we don't have to worry about the y components anymore, just the x components, because that is the only force right here that our observation point is feeling is going to be in the x direction, because the y components cancel out due to symmetry. All the y components from all the lines of charges up here are going to cancel out all the y components from the lines of charges here on the bottom of the circle. So let's get to it. Up here, as I said earlier, dq equals lambda r d theta. So we're just going to make this a dE now. Equals k lambda r d theta over r squared. We're not changing anything right there yet. Okay. So let's move on. This is the point where you would either go differentiate for your x components, your dex and your dey, but since we already said that the y components cancel, we don't need to do the dey. So let's just do the dex. It's going to be equal to k lambda r d theta over r squared. So right now we're going to be doing similar triangles to make our cosine phi here make sense as to why it goes right there. So up here, we're going to use similar triangles to find this dex. That's what we want. So here we go. Cosine phi is equal to z over the square root of z squared. I'm going to explain this, plus r squared. So as you know, cosine is equal to adjacent over hypotenuse. If you can see that. Cosine is equal to adjacent over hypotenuse. Okay, stay with me. So the adjacent to phi right here is the dex. The adjacent to phi here is z. The hypotenuse of phi right here is de. The hypotenuse of phi right here is the square root, sum of the squares of z and r, to find this length right there. So because of similar triangles, you can simply use the cosine values of this triangle right here in place of the cosine values of this triangle here, because of the ratios given by the similar triangles. You can simply plug it in right here, this cosine phi value, and it'll give you your dex component, your ex component. So let's continue on. We're just going to be subbing in this component here into our formula. So dex is equal to k lambda r d theta over r squared z over z squared plus r squared to the 1/2 power. R is your distance from the charge to the point of observation. So that would be the charge to the point of observation. So that would be this length here. And we already have that length right here. We already did square some of the squares. So r is equal to square root z squared plus r squared. Because right here, r squared, we can simply state that dEx is equal to k lambda r d theta over z squared plus r squared times z over z squared plus r squared to the 1/2 power. See that? So we're just going to combine this all up and state that dEx is equal to k lambda r z d theta over z squared plus r squared to the 3/2 power. That's 3/2 because this is 2 over 2. 2 over 2. And you're adding a 1/2. 1/2 right here equals 3/2. So from there, we are going to integrate it to be we can just say right here, you know what, hey, we're integrating now. Integrate. We're integrating values from 0 to 2 pi because we're going all the way around the circle. You know, if it was half a circle, it'd go 0 to pi, 3/4, some fraction I don't want to do right now because I'm brain dead. Anyway, we're integrating, so now we're going to have Ex equal to k lambda r z 2 pi over z squared plus r squared to the 3/2 power. See that? That right there is your final answer, everybody. Box that puppy up. I know it says Ex, like it's the X component, and you would think like, oh, the E field has X and Y components. Here, let me move this around a little bit. But the thing is, right here, we already stated that the Y components are canceled out, so there is no Y component. So if you were going to sum up your, E is equal to your I hat plus your J hat, you'd only have an I hat there. Your I hat being this puppy right here. So that's it, everybody. That's your E field for a distance z of a circle on axis, of a ring of charge on axis, excuse me. Enjoy your evening.